Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture we completed the intra-block analysis of variance of an incomplete block design. Well, when we were trying to develop the analysis of variance, then we had not talked about whether this is intra-block or not, or are we going to call it as intra-block analysis of variance or not. So, now the first question comes, how this intra-block analysis name suddenly cropped up. So, in this lecture today, we are going to talk about interblock analysis of an incomplete block design. And based on that, we can also have interblock analysis of variance. So, now once we are going to introduce the concept of interblock analysis of variance, that means there also exists an intrablock analysis of variance. So, that is why the analysis of variance what we have developed up to now, that means we are trying to write down the normal equations, we are trying to eliminate the block effects to estimate the treatment effects, or we are trying to eliminate the treatment effects to estimate the block effects, and then we are trying to find out the treatment sum of squares, block sum of squares in terms of adjusted versus unadjusted. Based on that analysis, whatever analysis of variance we had obtained, that is going to be called now as intra-block analysis of variance. So, now the next question comes, once we have completed the analysis of variance, why are we thinking about the interblock analysis of variance? Because up to now when we did the one-way, two-way analysis of variance in the case of complete block design, then we had not talked about it. So, definitely now you have learned all the things, and our objective is that we are trying to improve the statistical inferences. So, we are now going into more deeper. So, the first question comes here, that what is the interblock analysis? So, now let me try to give you a very simple idea, and I will also try to now explain you what are we going to do in this lecture and in the next lecture, because both of them are going to be interconnected. And in fact, they are also going to be interconnected with the intra-block analysis of variance also. So, now you see, whenever you are trying to conduct an experiment, what is your objective? Your objective is to compare various levels of the treatment, and you want to see that which levels are having the same effect, similar effect, and which are different. And your basic objective is that you want to have an outcome where the variability due to randomness is as minimum as possible. So, what you try to do? The variability in the randomness is being indicated by the variability in the observed values in your symbol, that was Yij's. And that is why if you try to see, variance of Yij was the same as the variance of epsilon ij as sigma square, because epsilon ij's are the random quantities that you cannot observe, but Yij's are the observable values. So, now in order to have your statistical inferences with a smaller variability, you divided the experimental unit into different blocks, and then you had partitioned the total sum of squares into sum of square due to block, due to treatment, and sum of square due to errors. Now, when you are trying to allocate different treatments to the blocks, you basically assume that the block totals are not having any effect of the treatments. But in practice, it may be possible that when you are trying to construct the blocks, then the block totals may also contain some information about the treatments. And when you are not considering it, that is getting lost. And now you have no idea that how much information is getting lost due to this fact. So, the next question comes, can we use this information? How? For that, first we need to know how we are going to recover that information, and once you obtain it, the next question comes, how would you like to use it? So, this job is being done by the interblock analysis of variance. So, in order to retrieve the information about the treatment totals from the block totals, we have to do something. So, what we do here, that we try to assume that my block effects are random. Now, you can see, if you are trying to think about the two-way analysis of variance model, then what will happen? Your treatment effects are going to be fixed, but your block effects, now you are assuming them to be random. Now, if you try to recall, in the beginning of this course, we have discussed about fixed effect model, random effect model, and mixed effect model. So, now in this case, what will happen? You will have a factor which is random. So, now we have to see how to handle that condition. So, now what are we going to do here? That because we are going to assume now that the block effects are going to be random. So, that means they will be indicated by their variances, say sigma square beta, for example. So, as you have done that, when you are trying to consider a random effect, then in that case your objective is to estimate the variance of the random effect. Whereas, when you are trying to consider the fixed effect model, then you are trying to estimate the fixed parameters and the random error variance, right. And in the case of random effect model, you are trying to estimate the variance of the random effects and the random error. So, now in this lecture, we are going to learn that how we are going to modify this setup, and we are going to use here the concept of random effects, and then you can ask me why I am doing it. So, if you go back to your original objective, we had discussed once that when we are trying to conduct the test of hypothesis for the treatment and block effects, we are usually more interested in the treatment effects, and that is why we are trying to estimate them, and based on that we are trying to construct the setup for the analysis of variance. So, that is why we have developed the intra-block analysis of variance. Now, we want to improve it, because we believe that some information is being contained inside the block total. So, we will try to utilize use this information, and then we will try to estimate the treatment effects once again. But in this case, what will happen? Now the treatment effects are going to be estimated when the block effects are random, and earlier when you estimated the treatment effect, that was the case when your block effect was fixed. So that will be called as intra-block estimate of the treatment effect, and this will be called as an interblock estimate of the treatment effect. And based on that you can conduct the analysis of variance also. But my objective here is different. My objective is to use this information to improve the analysis of variance. So what I try to do here, that earlier we had estimated the treatment effects using the intra-block analysis of variance, and now we are trying to estimate the treatment effect once again using the interblock analysis. Now you have one parameter, but you have here two estimators. Then we have to think that how to combine these two estimators together in an efficient way, because definitely you have the one parameter tau, and tau is not asking you that whether you should estimate me by intra-block analysis or by interblock analysis. This is only we people who are going to take a call that how are we going to estimate the treatment effect tau. So now we have to think about an approach by which we can combine the intra-block and interblock estimates of the treatment effects together. So now what will happen? Then you will have only one estimator of the treatment effects, and then using that estimator we will try to develop the analysis of variance, and that will be called as intra-block analysis of variance, or since we are trying to recover the information about the treatment from the block totals, so this is also called as recovery of interblock information. So that is our objective that we are going to finish in this lecture and in the next lecture. One advice to you all, that when now we are going into more details, you will see that towards the end the things are becoming little bit complicated, but we are not allowed to escape. We have to solve the problem. In case if we cannot solve in the best possible way, we will try to make the best possible approximations. So towards the end, be mentally prepared that when we are going to talk about the recovery of interblock information, we are going to use some approximations. At that moment, I may not have the exact expression for those things, but I will try my best to convince you that how to think so that these approximation will at least appear good. And based on that, we will try to develop that how are we going to get the solution. So that is what we are going to do in this lecture and in the next lecture also. So let us try to begin this lecture, and first we try to understand that why do we need this interblock analysis, because it is very important for you to first convince yourself that why you are trying to do it. So I will try to take here a simple example to show you that why do we need such a setup which gives us an idea that if we try to consider the block effect to be random, possibly that is going to be helpful. So let us begin our lecture. Okay. So now we begin with an introduction to the interblock analysis of variance. Right. So you see, the objective or the purpose of the block design is to reduce the variability of a response by removing the part of variability as block numbers. right. And in fact, if this removal is illusory, that means it is only appearing and the block effects being all equal, then the estimates are less accurate than those obtained by ignoring the block effect and using the estimate of the treatment effects. On the other hand, the block effect may be important, they may be marked. So, in this case, if the block effect is very marked, then the correction in the basic variability may be sufficient to ensure a correction of the actual variance for the block analysis. Now, when we had considered the intra-block analysis, then we had considered essentially the intra-block analysis for the treatments. Then, if you remember, we had obtained the reduced normal equations and which were obtained in two possible ways, that we try to eliminate the block effects and then we try to estimate the treatment effects, or the second option was that we try to estimate the block effect after eliminating the treatment effects. So, we had essentially considered, or we were more interested in the case when the treatments effects were estimated after eliminating the block effects, because we are more interested in the analysis of variance for the equality of treatment effects. So, now in such a case, if the block effects are marked, then the block comparisons may also provide information about the treatment comparison. So, obviously, a natural question arises here, how to utilize the block information additionally to develop an analysis of variance to test the hypothesis about the significance of the treatment effects. So, remember, we are still interested in the null hypothesis for the treatment effect, but we want to use the information about the block totals also. Right. So, such an analysis can be derived regarding the block effect as random variable. How? Because I will try to show you. Right. So, when we are trying to assume that the block effects are going to be random, this means that we are going to have the random allocation of different blocks of the design to be the blocks of the collected material. That means, you are trying to collect at random from the population of the possible blocks. And yes, means about the treatment, there is no doubt. The treatments are going to be allocated this at random in a block, right. So, that is going to be in addition to the random allocation of treatments occurring in a block to the units of the blocks selected to contain them. So, as we have done earlier, means in every block we were randomly allocating the treatment. So, that process will continue, there is no problem in that one. So, now if you try to see that, means earlier, if you remember, in the case of intra-block analysis, when the block effects were fixed, all the observations from within the block, they were uncorrelated. But in this case, when you are trying to consider the block effect to be random, then the two responses from the same block are correlated. Why? Because the error associated with each contains the block number which is common to both, right. And such an analysis of incomplete block design is termed as interblock analysis. Now, let me try to take here a very simple example to illustrate what I am trying to say and how one can say that the block totals are going to consider the information about the treatment totals, right. So, we consider here a simple setup where we are trying to consider 4 treatments, and these 4 treatments are allocated in 2 blocks, right. And with this setup, we will try to have an idea about why we are trying to propose this interblock analysis to be conducted in this way, and how the block comparison also contain information about the treatment comparison. How are you getting such an idea? So, you can see here I have taken here two blocks, block 1 and block 2. So, suppose in the block 1, means if you remember, you had denoted the observations as here y I j. So, you have here block number here, I goes from here 1 to 2, and then j is going from here 1 to v, and then out of those v treatments you have allotted 4 treatments to these two blocks at random. So, the block 1 contains here the treatment number 4, 6, 7 and 9, and based on that you have this observation y14, y16, y17 and y19. And similarly, in the block number 2, you are trying to give here the treatment number 3, treatment number 5, treatment number 6 and treatment number 7, and based on that you have the observations here y23, y25, y26 and y27. Now, we try to obtain here the block totals. You know how to obtain the block total. You simply have to sum all the observations inside the block. So, if you try to sum here all the observations which are inside the block 1, like as y14 plus y16 plus y17 plus y19, this is going to give you here the B1, you can see here. And similarly, when you are trying to add here the observations in the block number 2, that is y23 plus y25 plus y26 plus y27, this is going to give you here the block total number 2. So, now you have here these two block totals B1 and B2. Now, as you have said that you are trying to create here the blocks, you have created here these two blocks, block 1 and block 2, and then you have here treatments. So, definitely what do you expect? What type of linear model is going to represent this phenomena? Obviously, we have to consider here a two-way analysis of variance model or two-way model, where you have here two effects, which is beta I and tau j, right. Means at this moment means I am not considering anything to be random, I am simply trying to go with our classical methodology that we have learnt up to now. So, now if you try to consider the model here y I j is equal to mu plus beta I plus tau j plus epsilon I j, where you are trying to say that suppose I is going from 1 to 2 and suppose j is going from here 1 to 9. So, you have here tau 1, tau 2, tau 9, right. And out of those 9 you have selected 4 treatments, say here tau 4, tau 6, tau 7, tau 9 for the block number 1 and tau 3, tau 5, tau 6, tau 7 for the block number 2, no issues. So, now the observations in the block number 1, they can be represented as here, see here y14, which is equal to here mu plus beta 1 plus tau 4 plus epsilon 14. So, this 1 and 4 they are indicated, going to indicate the block effect to be beta 1 and the treatment effect to be here tau 4. So, you are assuming that once you have here two blocks, their effects are indicated by beta 1 and beta 2, right. So, similarly for all the observations which are contained inside the block number 1, this mu will remain the same, the block effect beta 1 will remain the same as beta 1, only the treatment effects they are going to be changed, tau 6, tau 7, tau 9, and obviously the random error component they will also be indicated by epsilon 16, 17 and 19. So, based on that now you have expressed the 4 observations in the block 1 y14, y16, y17 and y19 in terms of the linear model. Now, the same exercise you can also do for the block number 2. So, the block number 2 has the block effect beta 2. So, you can write down here the observation y23 as here mu plus beta 2, beta 2 means this 2 and this 2 they are going to indicate the block effect, and then the treatment number 3 is given for this observation. So, this 3 is coming over here y23 and plus epsilon 23. So, y23 can be expressed as mu plus beta 2 plus tau 3 plus epsilon 23. And similarly, you can express the remaining 4 observations here like this. y25 will become mu plus beta 2 plus tau 5 plus random error component. y26 will become mu plus beta 2 plus tau 6 plus epsilon 26, and y27 will become here mu plus beta 2 plus tau 7 plus epsilon 27. right. Now, up to now there is no problem. So, now what we try to do here, that we try to obtain here the difference of block totals, that is B1 minus B2. Now, how you are going to obtain the B1 minus B2, that you already have seen here. So, you simply have to replace this y14, y16, y7, y19, y23, y25, y26, y27 by these expression what you have obtained here. Just try to do this simple algebra, and you can see here you are getting here this type of expression, which is 4 times beta 1 minus beta 2 plus the sum of the treatments in the block number 1 minus the sum of the treatments in the block number 2 and plus the random error components here. Now, in case if you try to observe this expression of B1 minus B2, right, you can see here that this is containing two types of information, beta 1 and beta 2, as well as this treatment effects. Well, in case if you try to take here expected value of beta B1 minus B2, then if you are assuming that beta and tau they are constant, they are fixed effect and they are from the fixed effect model, and the usual assumption is that expected value of epsilon ij is equal to 0. So, this term will become simply here 0, right, no issues. But now, if you try to see this expected value of B1 minus B2, that is also containing the block effects, and that is also containing the treatment effects. Now, tell me one thing, what you were trying to do? You were interested in comparing the treatments, and you believe that the treatment totals are the quantities which are going to contain the effect about the treatment effects, and you assumed that the block totals are going to give you the information only about the block effects. But you can see here in this case, in this situation, this block totals, and if you try to take the difference of them, means they are also containing the block effect as well as treatment effect. So, one option that you can have here, that if you want to make this block effect to be 0, one option is that if we can simply assume that the block effects are random and they have got mean 0. That means, just like your here expected value epsilon ij to be 0, you assume that expected value of beta 1 is equal to 0 and expected value of beta 2 is equal to 0. Yes, you can also ask me at this stage, well, why you are trying to take it 0, why not you are trying to take it to be same here as say beta, because that will also give here this term expected value of beta 1 minus beta 2 to be 0, but this I am not doing here because of any reason. That will, yes, that's a that's an idea, but we are going to consider about this idea after some time, and I will consider it, I will explain you and I will inform you, right. So, now you can see here, if you try to assume here, in case if expected value of beta 1 and beta 2 are 0, that means beta 1 and beta 2 are random with mean 0, then in that case this expected value of B1 minus B2 can be obtained here as a tau 4 plus tau 9 minus tau 5, and the remaining treatment they will be getting cancel out, right. You can see here that this tau 6 and tau 7 they are cancel out with here this thing. So, now if you try to see, this is reflecting, if you try to look at this expression, you are trying to compare the block totals, but they are also containing the information about the treatment. So, this reflects that the block comparison can also provide information about the treatment comparisons. And now, the question is how to do it, right. So, this intra-block analysis of an incomplete block design is based on the fact that we are trying to estimate the treatment effects or their contrast by eliminating the block effects. But now since different treatments occur in different blocks, so one may expect that block totals may also provide some information on the treatments. So, the interblock analysis utilizes the information on block total to estimate the treatment differences, right. So, that is what we are trying to do now here. And now we are going to assume that the block effects are random. So, now you have here two parameters beta and tau. So, if you are trying to assume beta is random and tau is fixed. So, this is obviously the setup of the mixed effect model in which the treatment effects are fixed, but the block effects are random, right. So, now there will be some change, and if you try to see many times I have told you that we are going to consider the fixed effect model only unless and until I say that now we are going to consider the random effect model or mixed effect model. So, now after I complete this specification and the utility or the idea behind this interblock analysis, then I will try to create here a random effect model, and then we will try to see that since one parameter will be random, another will be fixed. So, essentially we will be working in a mixed effect model. So, as soon as I start it, I will explain you, but at this moment we are not considering. Okay. So, now this approach is applicable only when the number of blocks is more than the number of treatments, right. And now we can develop here this interblock analysis of variance for the general setup here when we have say this K1, K2, Kb, they are different or Nij can take any value. But here in this case we are trying to assume that we are going to consider here a design in which Nij can be 0 or 1 only, and all K1, K2, Kb they are going to be the same here as say K. That means, all the blocks they have got the same number of plots K, and this is a binary proper design, means this Nij can take here only two possible values 0 and 1. So, we know that when Nij equal to 0, that means the treatment does not occur in the block, and when Nij is equal to 1, that means the treatment occurs in the block. Now, one point where you have to be little bit careful. You are trying to assume here that all K1, K2, Kb they are going to be the same as here K, but now you can see here K is here a scalar, and this K is not the vector say K1, K2, Kb, right. If you remember, in the case of intra-block analysis of variance, you had indicated by K the column vector of K1, K2, Kb. But now we are assuming this K1, K2, Kb to be the same. So, you have to be little bit careful when we are trying to specify now the model. Right. So, okay, now we come to the setup of model, and then we are going to estimate the parameters. So, now this Yij is going to indicate the same, that is the response from the Ga treatment in the ith block, and then we have here the model Yij is equal to mu star plus beta I star plus tau j plus epsilon ij. I goes from 1 to b, j goes from 1 to v. So, you can see here that I have indicated this general mean effect by here by mu star, which is different than the Lear general mean effect. And now we are assuming this block effect beta I to be random. So, I am indicating by here beta I star, and this is going to be the random additive ith block effect. And about tau j, there is no change. Tau j is the jth treatment effect, and this is actually fixed additive, and epsilon ij, they are also the same as earlier. They are the identically and independently distributed random errors following normal distribution with mean 0 and variance sigma square. Now, you have to just keep in mind that sigma square is going to indicate the variance of random errors, right. Now, Since we are going to consider here that the block effects are now random, so we have to assume or associate a distribution with beta I star, and we need to have some assumptions on the properties of beta I star. So, we assume here that in addition that we have epsilon ij's or iid following normal 0 sigma square, we have here the random effect beta I star, means I goes from 1 to b, they are independently distributed following a normal distribution with mean 0 and variance sigma square beta, and we are assuming that they are uncorrelated with epsilon ij also. Means you will see that if you do not assume that there are going to be some more terms, and they are going to make the analysis complicated. So, that is why just for the sake of statistical simplicity, we are assuming that they are uncorrelated, right. Now, one thing you have to keep in mind here, that when we consider the fixed effect model, then we had estimated beta I, and we had the condition like summation beta I equal to 0, or equivalently here that will be summation beta I star equal to 0. But this type of assumptions we cannot assume in the case of random effect models, because beta I is a random quantity. Random quantity cannot be estimated, that is a random variable, right. So, instead of assuming this type of condition that summation beta I star equal to 0, instead we assume here that expected value of beta I star is equal to 0, that means beta I star has got the mean 0. And in the case of fixed effect model, we had assumed that all yij's are independent, but in this case now yij's are no longer independently distributed, but we assume here that variance of yij is now becoming here sigma square beta plus sigma square, right. If you can see here that variance of yij will become here variance of here beta I star plus variance of here epsilon I star epsilon ij star, and plus there will be here covariance term. So, this covariance terms will come if you do not assume that this beta I star and epsilon ij are independent. So, we assume that one. So, in this case the covariance between yij and yi prime j prime, that will come out to be here sigma square beta if I is not equal to I prime and j is not equal to j prime and 0 otherwise. So, now we have this setup. Now, under this setup, now we have a different type of model, and we are interested in the block totals. We are no more interested in the yij's, means in the case of fixed effect model we were considering the yij's, but in case of this interblock analysis model where we are trying to assume this beta I to be random, we would like to consider here the block totals bi in place of yij. So, now we are going to express here in terms of bi. That is one of the basic difference between the approaches that we use in the case of fixed effect model and this model. So, now if you try to recall how you had defined the bi, that is the ith block total, that was summation over j goes from 1 to v and ij yij. Now, you have to express here, or you have to substitute here this yij, which is here mu star plus beta I star plus tau j plus epsilon ij. Now, in case if you try to open it, what will happen here? The first term will become here mu star summation over j and ij, and so this is here k. So, I am writing out here k mu star, and then in case if you try to consider here this term first. So, this will become here summation nij tau j. So, this I am writing now here, and then we try to consider here the term here whatever is now here left. So, you can see here this two terms are left. So, this will become here summation over j and I j beta I star plus here summation over j and I j say epsilon I j. So, now you know that this term is going to be here k. So, now I try to represent this entire term as here say f I, which is given here. And you can see here that I is going from here 1 to b. So, now you can see here that here in this case this beta I star is random, epsilon I j is also random. So, do not you think that if you try to look at this model b I is equal to k mu star plus this summation over j n I j tau j plus f I, do not you think that it looks like as if we have got here a model something like b is equal to x beta plus some here f, just like you had y equal to x beta plus epsilon, right. So, this quantities which are here indicated by here FIs, they are independent and they have got a normal distribution with mean 0, and variance is given by k square sigma beta square plus k into sigma square, and this quantity I am indicating by here sigma square f. So, that is going to indicate as if this is the variance of the new type of random errors f I. But you can see here one thing, if you are aware about the theory of linear models, right. So, you can see here that if you can express this framework what you have obtained here in the form of a setup of a multiple linear regression model, then you can obtain the least square estimates of the parameter vector. So, that is what I actually am trying to now do here. So, you can see here now in this case, if you try to look at this structure from the linear model point of view, the expected value of b I comes out to be k into mu star plus summation j n I j tau j. It is just like if you have you had obtained expected value of y equal to x beta type of thing, right. And variance of b I is coming out to be here sigma square f. It is something like you had done in the case of linear model as a variance of y I is equal to sigma square. And then you had assumed that covariance between y I and y j is equal to 0 in the case of linear model. So, similarly, you have here covariance between b I and b I prime is equal to 0, right. So, now in case if you try to rewrite this model in the form of vectors and matrices, which is now very easy for you that you already have done. So, if you have practiced those things, you can write down here all these equations which you have obtained here. If you try to see here, this is your b I and I is going from here 1 to b. So, you have here a model like b 1, b 2 up to here b b. You try to write down here all the equations and then you will have here say f 1, f 2, f b, right. So, you can write down here b is equal to k mu star e b 1 plus n tau plus f, where f is going to be the vector of order b cross 1 of this random error. Now, you have obtained here a model like this. Now, if I ask you, do you remember that when you considered the multiple linear regression model y equal to x beta plus epsilon, then you had obtained the normal equations after minimizing the sum of squares due to random error as say here x transpose x beta is equal to x transpose y, and then you had pre-multiplied with the inverse of x transpose x on both the sides, and then you had obtained the ordinary least square estimator from here as a beta hat x transpose x whole inverse x transpose y, right. So, now if you try to rewrite this equation in the framework of y equal to x beta plus epsilon type of thing, then what do you see here? And if you try to see, this normal equation was obtained after minimizing epsilon transpose epsilon, which was here y minus x beta transpose y minus x beta. So, I can now apply here the principle of least square, and I can minimize this quantity B minus K mu star EB1 minus N tau transpose, and the same quantity here B minus K mu transpose EB1 and transpose. So, if you try to see, this is a quantity like F transpose F, and we try to partially differentiate with respect to mu star and tau, and you will get here this type of normal equation. What you have to do here, simply remember that in this model you are trying to get the normal equation here as, say, x transpose x beta is equal to x transpose y. So, you have to simply do this small exercise. You have to just express these terms in terms of x and y, and then just substitute it here. And once you try to do it here, you will get here this equation, right. So, you can see here, this is something like your here x transpose, this is something like here x, and this is something like your here beta, and this is something like your here x transpose, and b is something like here y. That is all. And after this, you simply have to just multiply and simplify it. So, if you try to just multiply these matrices together, you will get here this equation, and now you know what is the value of E transpose B1 into EB1, that is simply your here B, and right, and then you are trying to use here this result here, N transpose EB1 is equal to R capital R into EB1. So, you can use here these things, and you can write down here this quantity and this quantity here as like this, using this relationship. And then means everything remains the same, and now you try to obtain here two sets of equation, which I am trying to number them as 1 and 2. Now, your objective is very simple. You want to obtain here the estimates of mu and tau, which are indicated by here mu tilde and tau tilde. So, now if you try to see here, you just cannot obtain here the estimates directly unless and until you try to use here a side condition. So, we assume here that E transpose V1 R tau tilde is equal to 0. So, you can see here that I am trying to make this term to be equal to here 0, and actually this term is equivalent to write writing summation over j r j tau j tilde is equal to 0, and means and we have to assume that N transpose N is a non-singular matrix, so that I can take its inverse. So, from this equation number 1, you can see here, if you try to put this term to be 0, then you can obtain here the value of here mu tilde as say here g upon bk, and then you try to obtain this value of mu, and then try to substitute it here in the equation number 2 and try to solve it. So, this will give you the value of here tau tilde, that is an estimator of tau. So, you try to obtain the estimator of mu as mu tilde, try to substitute it in the equation number 2, and then try to obtain the estimator of tau as tau tilde. This will come out to be here N transpose N whole inverse N transpose B minus R EV1 G divided by B. Now, you see, this is the interblock estimate of the parameter tau. Now, we just try to simplify it further, so that we can obtain here some forms of this estimator, which are easy to use in the further analysis. So, what we try to do here, that we try to use here this relationship, that R EV1 is equal to say small r is equal to N transpose EV1, and we try to substitute here this R EV1 here, right, and then I try to multiply and divide by here k, right. So, now you can write down here this term here as say g upon bk into N transpose N EV1. Now, I try to bring this N transpose N whole inverse inside this bracket, and you can write down here N transpose N whole inverse N transpose B minus G EV1 divided by BK, and this is called the interblock estimate of tau, right. So, now you can see here that now you have obtained here the interblock estimate of the tau, and but now if you try to see what was your objective, that now using this interblock estimate of tau, you can also develop so called interblock analysis of variance. But if you try to see what are we trying to do here, we are trying to develop here an analysis of variance for the treatment effects, and we are trying to improve the intra-block analysis of variance. So, now we have got here one more type of estimator of tau. Based on that, we have here interblock analysis of variance, but we want to go further. We want to utilize the information which is contained in both the intra-block estimate and the interblock estimate together, and based on that we will try to conduct the analysis of variance, so that the resultant analysis of variance will have both type of information, from intra-block analysis of variance as well as from the interblock analysis of variance. So, we want to utilize the information from interblock analysis along with the intra-block information to improve upon the statistical inference. So, now we have obtained the interblock analysis estimate of the treatment effect, or we have obtained simply the one more estimator of the treatment effect tau using the interblock analysis. So, the next question that comes before us, that how to use this information for the improved estimation of the treatment effects and use it further for the development or the test of significance of treatment effect, that is your analysis of variance, right. And now, in case if you are able to obtain this type of analysis in which you are trying to use the intra-block estimate of treatment effect as well as interblock estimate of the treatment effect, then definitely you are trying to use more information. So, we expect that the statistical outcome or the statistical inferences, what are you going to obtain from there, they will also be improved, right. So, now we come to an end to this lecture, and you can think here that why I am not conducting here the interblock analysis of variance. So, I have given you the reason. If you wish, you can read from the book, you can do it, but since my objective is to do something else, so that is why I am not doing here. But it does not mean that this is difficult or we do not want to do it. It is as simple as it's I want to develop an analysis of variance by using both the information together for the treatment effects. So, that is why I am stopping here, and then I am not giving you here the interblock analysis of variance. Now, the next question comes here. How are we going to combine them together? We have to first find an estimator of tau that can combine the intra-block estimate of treatment effects and interblock estimate of treatment effects in such a way such that we get a single estimate of the tau. And then we have to think that how are we going to develop the analysis of variance. So, up to now there was no complication, everything is simple, straightforward, following the statistical law, but when we are trying to do the analysis of variance by joining the two estimators, possibly we may have some complications, and that we will try to see how we can take the best out of that. So, now I would request you that you please try to revise this lecture, try to understand why are you trying to do this interblock analysis of variance. And once you are convinced about this, then going for the recovery of interblock information will not be difficult. So, I stop here, you please try to revise, and I will see you in the next lecture. Till then, goodbye.